Okay, so our class is now being recorded and you should be able to see my screen as well. Uh, I think still a minute. We'll just wait for another minute and then start. Okay, yeah, it's 3:40. I think we should start. Okay, so once again, good afternoon, good evening to everyone joining in. Welcome to the second class of our course on network fundamentals for cloud. Quick recap of where we were last time. So we had started with the topic of network fundamentals, and in the network fundamentals, we started by looking at the nuts and bolts view of the most commonly available and used network, which we call as the internet. And when we looked at the internet, we said that the internet, from a layman perspective, from a devices perspective, appears like a very abstract boundary edge, at the edge of which we have these hosts or devices called the end systems, within which are network appliances called packet switches. I mean, they can be switches or routers, and we did not distinguish between the two at this time. We said there are some kind of network appliances which are involved in the forwarding of data packets. And these network switches or packet switches are themselves connected via communication links, which could be wired communication links or wireless communication links. And we had also digressed a lot last time to discuss how the transmission rate, sometimes also called the capacity or the throughput of a communication link, is directly proportional to its bandwidth. And we tried to draw an analogy where we said the bandwidth is more like characterizing the thickness of the communication link, whereas the throughput or the transmission rate is more like the volume of data that can flow through the communication link of a given thickness or bandwidth. And then at the end, we had said that even this abstract boundary of the internet is not a single network, it's actually a collection of networks. We characterize the three types of networks within the internet as the access network, the core, and the edge. So we basically said the network edge is where the host resides. The host could be clients or servers. And we also said that servers are often in data centers. I mean, it's not always true, but often you'll find servers installed in some data centers, even in either in private data centers belonging to a specific organization or in some public data centers. And so the access networks are which are the first point of connect for the edge devices. They provide the first network connection to connect to the rest of the internet, and that's what we call as the access network. And then there is the core part of the internet, which is consisting of primarily the ISPs, which could be local or regional ISPs, or then the next level of ISPs, which are called the national or global level ISPs. So in that sense, we said that the ISPs are basically the backbone of the internet. They are the ones who connect the internet. The core part of the internet, which is primarily consisting of these ISP areas, contains a mesh of interconnected routers. And these routers are primarily involved in doing the packet switching, the forwarding of packets from one access network to the other access network, so that the traffic can flow from the source to the destination. So this is where we were last time, and I think we can continue forward from here. Okay, so if we look at the network core, which as we just said is the ISP network, the local, regional, and then the national and the global ISPs, there are two key functions that the network core performs. Okay? One is called the function of forwarding. Okay, so what is forwarding? Sometimes in literature, the term forwarding is also called as switching. Okay, so what is forwarding? It's a local action which is performed by every network switch in the network core, where when it receives a packet on one of its input links, it decides how that packet needs to be forwarded, okay, to one of its output links. Okay. So in this diagram, for example, we see that a packet, a blue colored packet over here, this is a data packet. A blue colored data packet with a green colored packet header is arriving on a network switch. Now, the network switch will look at the packet header, which is the green part of this blue colored packet. In this packet header, one of the key fields that the network switch looks at is the destination address, which is what? The address of the edge device to which this packet is destined towards. So this packet needs to reach the destination, and the address of that destination is included in the header of that packet. So any network switch in between will look at the destination address in the packet header, and based on this destination address, it will decide which output link. In this case, we see there's an output link called one, numbered as 1, an output link numbered as 2, an output link numbered as 3. So this is the incoming link on which the packet is coming in. And the packet could go out on any of these 3 output links, 1, 2, or 3. Which output link should the network switch forward this packet on to is decided based on which link is the best link to choose to reach a particular destination. Okay. Now, how does the network switch decide on what output link to be used based on the destination address? And for this purpose, it uses a table which is called the local forwarding table. Okay. And the table is so called because the action that we are going to perform is called the action of forwarding. We are receiving a packet, we are forwarding it to the next network switch. Okay. Now, the forwarding table is a very simple table. The local forwarding table in each of these network switches is a very simple table. What it contains is the destination address that is contained in the packet header. In this case, we see there are different possible values for the destination address. And the table guides the network switch, telling it which particular output link it should pick based on the incoming packet's destination address. Now, in our example, the destination address is 0111. So if I look up the forwarding table, I'll match it against this entry. And I'll say, okay, if the destination address is 0111, then the packet should be forwarded onto output link 2, which means the packet will get forwarded onto this link, reaching the next network switch. The next network switch will exactly do the same thing. As you can see, this switch over here also has a similar forwarding table, a local forwarding table, using which it will decide how to forward it. Let's say it decides that this is the output link on which it has to forward the packet. Okay, the packet will reach the third network switch, which itself has another local forwarding table. It will also look at the forwarding table and decide how to switch the packet further. Maybe it's directly connected to the destination, and this is how the packet reaches it. Now, this action of forwarding, which is a local action, every network switch in the path from the source node to the destination node is looking up its own local forwarding table and deciding how to forward the packet to the next hop. And because every network appliance only worries about how to forward it towards the next hop, this whole action of packet forwarding in a packet switch network is also sometimes called as the hop by hop forwarding approach. So this approach of packet forwarding is what we also call as the hop by hop packet forwarding approach, which means one hop at a time. Every network switch looks at the packet, looks up the forwarding table, decides how to switch it to the next hop. And this is how the packet, using a hop by hop local forwarding action, eventually reaches the destination. Now, the most pertinent question at this point in time in our minds is, who fills this local forwarding table? How is this local forwarding table even created? How are these entries coming in the local forwarding table? So how are, for different destination addresses, the output link decided? Who fills this up? Now, in a very small private network, very small private network, it is even possible to hand fill the local forwarding table entries. When I say hand fill, an operator could use, let's say, a CLI interface to populate the entries in this local forwarding table. If this is what is done, then the local forwarding table is often called a static table. Static because I'm hand feeding as an operator via a CLI some fixed static forwarding entries in this table. As I said, this is possible to do in a very small network, where there are, let's say, only a few network switches, and I know what is the best path to take from a source to the destination. I can manually populate the forwarding tables in each of these network appliances as a network operator and make sure that the packets get forwarded from one source to the other destination in the most optimal manner. When I say optimal manner, following the best path in the network. But in larger size networks like the internet is, it's impractical to even assume that an operator will be able to manually fill up the local forwarding table in the thousands and tens of thousands of network switches that exist in the entire internet, right? It's not possible to do that in a large size network. So we need an algorithm. We need an algorithm, a computing algorithm, which can somehow determine for every pair of node. Let's say if I have a source node and a destination node, and if there was an algorithm which could run and decide what is the best possible path to take from a source to a destination, then that algorithm, a computing algorithm, could run, determine the path, and the path could be something like switch A should forward the packet to switch B. So source will give it to switch A. A should forward it to B. B should forward it to C, and C is directly connected to D, the destination. And this is the best path. Then the forwarding table will accordingly, the routing algorithm will accordingly fill the forwarding tables in switches A, B, C, such that if A gets a packet with destination address D, it should forward it on outgoing link towards B. If B gets a packet with destination address D, it should forward it towards the outgoing link C. And thereby, when the routing algorithm in this manner consistently populates the local forwarding tables in each of the intermediate switches, the entire end-to-end path will be kind of defined for the source to the destination. So this algorithm, which we are talking of, which has the ability to determine the path, best path or the most optimal path from a source to a destination, is what we call as the routing algorithm. Okay, so the routing algorithm, okay, is an algorithm which determines the end-to-end path. Okay, Sethi Appala Naidu, I've seen your question, but I'm purposefully waiting on it because in a few minutes I'll come back to it. Okay, I'll come to it. It will become clear what is the routing table, what is the local forwarding table. It will become clear in a while. Right? Okay, Raman, I'll come to your question as well. So right now, for all our discussion in terms of packet forwarding, there is no packet header update happening because right now we are only talking about one field in the packet header, which is the destination address. And the destination address will not change. It remains the same. So right now, just assume that the header is not being updated. Later, we will see that there are certain other fields in the packet header which are updated by every switch in between. And we'll talk about those slightly later. But for the function of forwarding, no, there is no update that needs to be done in the packet header. We're just looking at the destination address, and the destination address is fixed for the packet. It doesn't have to be changed. Okay, it's the end destination. So this is a local function, sometimes called the function of switching, which every uh, network switch is performing independently, individually, resulting in a hop by hop packet forwarding behavior. And what we just learned is that this local function of forwarding cannot work independently. It also needed a second function which must complement it, which is, as we said, the function of routing, which is what the routing algorithm does. Okay? So the function of routing, as we just said, is more of a global function. Just like the forwarding is a local action, every switch is doing it independently. Routing is more of a global function. Why is it a global function? Because as I said, what I have is a source node and what I have is a destination, and I have to figure out in a network what is the best path. You can see this red line. That's the path from the source to the destination. What is the best path to go from the source to the destination? It cannot be a local function. It's a global function. By looking at the entire network in totality, I have to decide what is the optimum path to take from the source to the destination. And this is, as we said, what the routing algorithm does. In a sense, what we are also saying as of now, and later we will change this, we will talk about other techniques. But for now, what we are also saying is that this function of routing, being a global function, because it's a global function, it must be implemented at all the network switches in the network. And this is what you can see here. This red part of every network switch. Right? Every network switch has a local forwarding table, which is being used by the local function called switching or forwarding, which is getting populated by a routing algorithm. But this is only one instance of the routing algorithm, which means the routing algorithm itself is a distributed algorithm. It runs at every network switch in the router. You can see this. This is another instance. This is another instance. So the routing algorithm, we call this algorithm as a distributed algorithm. The routing function is actually an algorithm which is a distributed algorithm. What is a distributed algorithm? A distributed algorithm by definition is an algorithm that runs across multiple distributed nodes and together decides the action that needs to be taken. So you will see that this part, the part of the routing algorithm, the red part, is running on every network switch. It's a distributed algorithm. Every network switch is running the routing algorithm. These instances of the routing algorithm running on each of these switches are communicating with each other, which means this routing algorithm running on switch A is talking to the routing algorithm instance running on switch B. This is communicating with this. Right? This routing algorithm is also communicating with the routing algorithm instance over here. So these routing algorithm instances running on each network switch are talking to each other. That's the reason they form a distributed algorithm. They communicate with each other. They talk to each other. And by talking to each other, they are able to determine what is the best path to take from a source to a destination. Which intermediate switches should the path go through before the source can reach, packets can reach from the source to the destination. Okay? So once the routing algorithm running this distributed function or global function is able to determine the source to destination path, that is when the algorithm will feed into the forwarding table at each of the nodes so that the path can be set up. And thereafter, the local forwarding action will consult this table, do a hop by hop packet forwarding, and the packet will flow from source to destination. So what we learned in this slide is that the forwarding or switching is a very simple function. It's more like a table lookup, you can say. I'm just looking at a header value called the destination address coming in the packet header, doing a lookup of this header in the table, based on table lookup, determining the output link, and then forwarding the packet on that output link. So it's a very simple function. Forwarding is a very simple table lookup kind of a function. But the more complex part that the network core performs is the function of routing, which is the function of determining for a pair of source to destination what is the best path that should be taken, accordingly populating the local forwarding tables. Now, if you try to map this with an analogy, okay, think of the road network routing problem. We are implicitly using this every day. Right? When we go from home to office, we always try to pick the path from home to office, which is the most optimal. Right? When I'm purposefully using the term optimal, because for different people, optimality means different things. The most optimal for some people could mean a path which has the least distance in terms of, let's say, kilometers or miles. For other people, most optimal path may be the one which takes the least amount of time to reach the destination. And when distinguish between distance versus time, the key factor could be what? Congestion on the roads. A path or a road, a path from my home to the office, a route, let me call it route. A route from my home to office, right, could be smaller, but may take more time because of congestion on that route. But an alternate route from my home to my office may be longer in terms of distance, but may be shorter in terms of time taken because of less congestion on that. Correct? So, what is it that Google Maps tries to do for us? Yeah, so Ramkumar, I'm just coming to that algorithm, the Dijkstra's. We will, in fact, come to that algorithm. Dijkstra's is one of the algorithms which is using. Amit, there are a lot of routing algorithms. I'm just introducing the topic of routing. And in a subsequent class, we will talk about routing algorithms, including how Dijkstra's algorithm, which Ramkumar just mentioned, is being used as a basis for some of the routing algorithms. So we'll talk about a lot of routing algorithms. Right now, I'm just defining what we mean by routing and why is it a global function. So as I said, with the analogy that we were just discussing, if I look at Google Maps and I say, okay, I want to go from my home to my office. What is Google Map trying to do? It's trying to solve a global function. It's trying to run a global function, the function of routing. It's not looking at, so it's what is it trying to do? It has a complete network view. What is that network view? It's the road network. Right? Think of the road network like a communication network. My home is sitting on a local road, internal colony road, let's call it, which let's say connects to a city road, which connects to a state highway, which probably connects to a national highway, and so on and so forth. Just like our communication network exists. Right? Now, when Google Map decides that I need to go from my source to the destination, which is from my home to my office, there are multiple paths from my home to the office. But it tries to solve the routing problem by looking at the entire view of the network, the entire view of the road network. It also looks at the level of congestion or the traffic on each of the roads. How much time is it taking for people to cross every road? And thereby it runs a complex algorithm which eventually gives me the best possible path. Sometimes it will show me more than one path. It will show so many kilometers on this path and this is the time, and so many kilometers on this path, this is the time. Based on my choice of optimality, I may choose a path which is shorter in distance, or I may choose a path which is shorter in time. Right? And then I'll follow that route. So what Google does is the global function of routing. So in this, we are seeing that if somebody wants to go from San Jose on the west coast of United States to Northampton, which is on the east coast of United States, the entire path that it takes from San Jose to Northampton is what we mean by the function of routing. It's a global function. Global because to determine the path, I need to have the global view of the network, the entire end-to-end view of the network. Okay? That's when I can decide what is the best path to take. Okay, so that's a routing is considered a global function. Whereas, so this is routing, determining the path from source to destination. Whereas once this path has been determined, right, what is the next thing that is happening? At every intersection, right, let's say there are multiple intersections, traffic intersections or roundabouts. What is a roundabout or what is an intersection? An intersection is where there is one incoming road and multiple exit paths from that intersection. Right? If there's just a single road, there's no exits or there are no exits, it's not called an intersection because we just have to keep going on that road. But as soon as there are certain exits, let's say 4 or 5 exits, that's an intersection. I have to decide if I'm coming down this path, this road, and then there are multiple exit paths. Which exit path should I take so that I remain on the end-to-end route? What is that? That's the local function of forwarding. So once I have the entire route, every intersection point in the road network is like what? It's like a network switch. Correct? Because just like every network switch has an input link and multiple output links, an intersection has an input road on which I am coming in, and there are multiple exits. So just like in a road network, I need to decide which exit to take to remain on the end-to-end route. In a packet switch network, when the packet enters into a network switch from an input link, the switch has to decide what output link the packet should be forwarded onto so that it can remain on its route towards the destination. Okay, so just like when I use Google Maps, the first thing Google Maps will do for me is run a global function called routing to determine the most optimal end-to-end path. Once that is done, each time I reach an intersection, it will tell me which exit to take. That's the local function of forwarding. This is exactly what is happening in a packet switched network. The routing algorithm is determining, it's a global function, it's determining the end-to-end path to be taken from a source to a destination. But once that is determined, it is populating the forwarding tables in each of the switches in between that path so that they can simply look at that table and do the simple function of table lookup and keep forwarding the packets, thereby implementing what we call as a hop by hop forwarding algorithm. A hop by hop forwarding algorithm. So this is how in a packet switch network, data traffic flows from source to destination, right? By following the twin functions of routing and forwarding. So routing is a global function, forwarding or switching is a local function. Okay, now, yeah, so let's see if I should answer some of these questions. So Seti Appala Naidu, is routing table and local forwarding table the same? For all our discussion right now, you can treat them to be the same for now. Okay, we will see later that the entire function of routing and forwarding, okay, um, can be implemented physically in a network appliance like the switch in different parts of the switch. When I say different parts, some functions like the global function of routing or the routing algorithm could be running in the host CPU or the host processor, whereas the table lookup or the forwarding function could be implemented because it's a simple table lookup. I can implement it in ASIC, in an application specific IC, right? So because the entire function could be implemented physically in different components of a network switch, either in a as a software in the CPU or as an ASIC, which is the hardware, which is you can see it as a hardware component of your network switch. The table could be duplicated or exist in multiple subparts. I mean, it could be split up and exist in different parts of your network switch. Okay, so we will come to that later. But for all current discussions, Sethiapala Naidu, you can treat the routing table and the local forwarding table as the same. For now, treat it as the same. It will simplify all our discussions. Later, when we get deeper into a network switch, when we look at its components, we will start to understand how the table could be split up into parts within the switch itself. Okay, we'll come to that later. Okay, okay, so packet header will be updated by each switch, that I already answered. For now, we will see answer to your question, Raman, is no. Later, we will see certain fields in the packet header do get updated, specifically the time to live. I'll introduce that later. What is the TTL value in a packet header? But we'll talk about that later. Okay, Ram Kumar's comment we've seen, Amit I've seen. Dayanand's question, what's the difference between packet switching and circuit switching? I think we do have some slides later, but okay, yeah, I think we have slides. We'll be coming to that part, Dayanand. In a while, I'll explain what is packet switching and circuit switching. But quick answer to your question right now, the internet or any data network, okay, is packet switched in nature most of the times, whereas a traditional telephony network, right, used to be circuit switched. Modern telephony networks, especially the mobile networks, are all becoming packet switched, but traditionally they used to be circuit switched. So traditional distinction between packet switching and circuit switching, as a very layman, I would say, was data networks were packet switched, voice networks were circuit switched. That distinction or that is no longer true today, but that I'll later come to when we start talking about in some subsequent slides what's the difference between packet switching, circuit switching. Right now, the simple answer to your question, Dayanand, is wherever you think of a data network, think of packet switching. Wherever you think of voice, traditionally used to be circuit switching. So if you look at plain old telephone system, the old telephony network, they used to be circuit switched. Okay, what's the difference? We'll come to it in a while. Slightly later down the line, we will talk about that. Okay, so essentially what we are currently talking about is the internet, and the internet being a data network, it's actually carrying data. We are talking about a packet switch network because it's taking chunks of data called packets and forwarding these packets from, or hop by hop forwarding these packets from source to destination. Right? So we call it a packet switched network. The data packets are getting switched through the network from source to destination. That's how it's called a packet switch. Okay. So right now we're discussing about packet switching. How does it differ from circuit switching? Slightly later down the line, we'll talk about it. Okay. So what is the function of the host? So we've said, okay, the core of the network, which includes these network switches, they are doing two functions. They're doing the local function of forwarding by looking at a forwarding table. They are also implementing a distributed algorithm called the routing algorithm, and together implementing a global function called the function of routing. So this is what the network switches do. What is it that the host is doing? The host has data which it is receiving from applications running on the host machine. it is taking that data or application data, right? So it takes the application message, breaks it into smaller chunks, which is what we call as packets. For our current discussion, for the sake of simplicity, we will assume that these chunks of packets are of fixed length called L. So L is the number of bits that are being carried in every packet of data. And as I said, this is only for sake of simplicity right now, for sake of discussion. There are different kind of packet networks, packet switch networks, and different types of packet switch networks do allow variable sized packets also, which means the length of every packet doesn't need to be fixed as L bits. Some packets could have L bits, other could have L minus, let's say 10 bits, other could have L plus 10 bits. So which means variable sized data packets are also allowed. It varies from protocol to protocol, different packet switch networks. For our current discussion, we're saying, okay, let's assume that the chunks of data, which we are calling as packets, are of fixed length of L bits. So the host machine, the end device, what is it doing? It's taking the application message, the data which the application is generating, breaking it down into smaller chunks of L bits each. We are going to call them as data packets. Each packet is going to be transmitted to the access network, to the first node in the access network, right? So that's what the host node does. The end device connects to the access network. So it takes the application message, breaks it into creates a packet of data out of it, and transmits that packet into the access network. Now, when it sends that packet to the access network, what is it that connects the host to the access network? The first switch in the access network, it's a communication link. This is the communication link. What did we say about the communication link? We said every communication link has a capacity or a throughput, or what we also call as the transmission rate, bits per second. It's transmission rate. Let's say the transmission rate of the link connecting the host to the access switch. The access switch is the name that I'm giving to the first switch in the access network. I'm calling it the access switch. So that rate is R, transmission rate is R. And every packet is of length L. What is the amount of time it will take to transmit this packet? What is the amount of time that the host will take to transmit this packet onto this communication link? That is what we call as the packet transmission delay. So understand this. I have L bits of data, and I have an outgoing communication link. So as I explained in the last class, that outgoing communication link has some link bandwidth, which is also treated like the thickness of that pipe. Now I may have a lot of volume of data in bits. Not all of it can be pushed all together into that pipe, because that pipe has only some thickness. It's like having, let's say, 10 gallons of water and a pipe which can only carry 1 gallon of water every second. Right? So it will take me some time to push 10 gallons of water through that pipe. Correct? That is what we are calling as the transmission delay, the amount of time it takes me to send the L bits of data or put those. Use the word, let me use the word put. I'm trying to put those L bits of data onto the communication link. How much time will it take me to put those L bits of data onto the communication link? The time taken will be L upon R. Because the communication link can carry or transmit R bits every second. I have L bits. So it will take me L by R seconds to transmit the entire chunk of packet onto this communication link. Okay, this is called the packet transmission delay. As we will see, it is one of the components of delay in any communication network, the packet transmission delay. As we see, it depends on the link capacity or the link transmission rate. how many bits per second it has. The larger the bits per second that it can carry, the smaller is the packet transmission delay. Okay, so this is simple maths. Right. Now, what is the hop by hop routing, or sometimes also called as the store and forward concept in a packet switch network? So in packet switching, we said a host takes an application message, breaks it up into lot of chunks of data packets of L bits each. So let's say the application message was 10L in size. The host will take this application message, break it up into 10 packets of L bits each. Now these 10 packets have to be sent towards the destination. What is the source doing? Every packet of L bits needs to be emptied onto the transmission links. As you can see, it's like volume of water. It's like a bucket of water carrying L bits. It's being emptied. This has already been half emptied and half is still pending to be emptied. Right? So it takes a host or a node L by R seconds to transmit or push out the L bit packet onto the link when the link transmission rate is R bits per second. Now these bits will flow over the communication link. Right? They will flow over the communication link, and when they flow over the communication link, where will they reach? These bits will start to reach the next switch, which is the access switch. And the access switch will keep collecting these bits. These bits of information are being pushed onto the communication link. They are flowing. For L by R seconds, this process will run. These bits will flow over the communication link and reach the next hop. Now the next hop, what will it do? It will keep collecting these bits until the entire packet has reached the next hop. Because what are we operating at? We are operating at the granularity of a packet. Right? So the entire packet has to be pushed. We are not dealing at bit level. We are dealing at packet level. Every packet, as we said, has a header. This is what we saw in the previous diagram. Every packet has a header. The header has the destination address. So the minimum granularity at which the forwarding function acts. The forwarding function acts at the granularity of a packet, not at the level of bits. So what we are saying is the bits, some of the bits of a packet may have reached the next hop. But this next hop switch cannot start transmitting these bits towards the next hop immediately. What will it have to do? It will have to wait until the entire packet has been received at the next hop. Once the entire packet is received, what will it do? It will look at the packet header, implement the forwarding function by doing a table lookup, decide what is the outgoing interface, and then start the transmission on the next interface. Okay, so this process where the next hop is first storing the bits until the complete packet is received, then implementing the forwarding function, and then transmitting the packet on the next hop. We call it the store and forward concept. Okay, what it essentially also means is that every network switch in the network, what should it have? It should have what we call as data buffers. It should have data buffering capacity, or it should have data buffers where it will hold the bits of information coming from the previous switch or host until the entire packet can be collected, and then that packet can be given to a forwarding function which will decide how to forward it towards the outgoing interface. So this storing happens in data buffers. The entire packet is received, it is stored in some data buffers maintained in these network switches, and then the forwarding function will forward the packet towards the next hop, and therefore we also call this process in packet switch networks as the store and forward process. Okay. Vipul's question, what will happen if packet loss happens? If a packet is lost at one of the switches during hopping, will it go back to the client? Okay. So we will come later to how lost packets are handled. For the sake of current discussion, where we are just talking about the functions of routing and switching, a lost packet from the purpose of routing function or forwarding function, a lost packet, or for that matter, an errored packet, a packet which has bit errors and cannot be transmitted any further. It's just lost. Think of it like a dropped packet. It will never reach the destination. Now, how do the higher layers above the routing algorithm take care of such lost packets? We will talk about that in later classes when we talk about transport layer protocol, TCP specifically. Okay, we'll talk about that later. For routing and forwarding function, a lost packet is lost. It's dropped. It will never reach the destination. Okay, so for all current discussion, a lost packet is just lost. Right? Routing or switching functions don't worry about it. If it's lost, it's lost. The application worries about it. The transport layer worries about it. We will talk about those slightly later. Okay. So this is how the packet switch networks operate in a store and forward manner. Okay. So this so let's look at some practical numbers. Let's say L is 10 kilobits. That's the number of bits, 10,000 bits, or 10 into 10 raised to 10 into 2 raised to power 10 bits are what are being carried in one packet. If the throughput of the communication link is 100 Mbps, which is normally what is the broadband connectivity we take at home, then the amount of time it will take your laptop to put 10 kilobits of packet onto the communication link will be L by R, which is 0.1 milliseconds. So it takes 0.1 milliseconds for one packet to empty out on the communication link. Okay. So the store and forward concept, as I just explained, is the concept that the entire packet must arrive at the next hop before it can be subsequently forwarded using the forwarding function. I can't treat it as bit stream, and I cannot start transmitting bits as they arrive. I have to receive the entire packet, store it in a buffer, then look up the forwarding table and then forward it towards the destination. This is how it works. Okay, so that's the store and forward. Aruna has a question. Is the store and forward at packet boundary? Yes, it is at packet boundary. As I said, it is at the granularity of packets. Does it forward as soon as the complete packet is received? It may not. Okay, so it depends on, we will talk about a concept called queuing in a while from now. So any intermediate switch like this may be receiving packets from multiple places. Okay, so what it may have is a queue of packets. Okay? When a packet arrives from source 1, another packet arrives from source 2, another packet arrives at source 3. There may be a queue of 3 packets. Okay? 3 packets waiting to be transmitted. Okay? So we'll talk about the concept of queuing. And the turn of the third packet will come only after the first 2 packets which were ahead of it in the queue have already been forwarded. So the answer to your question is no. It's not as soon as the complete packet is received, but it is sometime after the complete packet is received. Okay, so sometime after the complete packet is received will the action of forwarding happen. How much later? That depends upon the queue size. I'll just come to that in a while. Okay, so the queuing. But let's talk about simple concept first before we talk about queuing and all those things and the associated functions of queuing. Okay. So this is what is the store and forward concept. Okay. Yeah. Okay. So incidentally, the next slide itself was about queuing, and what you asked, Aruna. So this is what could happen. So in the previous example, we assume that this intermediate switch or access switch is only getting data from one source. But as I said, there could be multiple sources. In this example, A and B sending data to the access switch. Two computers could be connected to the access switch, and they could be sending their own data. One is green data, the other is blue data. Green is the A node, blue is the B node. Now, as packets arrive at the access switch, the store and forward function comes into play. Every packet is first received into an input data buffer. The entire packet is received. Once the packet is received, it's put into a queue. So there's always at this access switch a queue of packets which is waiting for the forwarding function to kick in. Right? So these are waiting to be transmitted towards the output link. Okay? So depending upon the incoming packet rate from each of these links and the processing capacity of your switch, the queue size could vary. You understand this? So think of any queuing. I think there are slides. Yeah, this is a queuing example. Look at a toll plaza. So a toll plaza often has a toll operator sitting. Depending upon the processing capacity or speed of the plaza operator and the rate at which cars are coming in, the queues will be formed. At peak traffic hours, cars are coming in at very fast rate. But this operator who's sitting at the toll plaza, he only has a fixed rate at which he can process or forward each car at a time. So think of the car as a packet of data. The toll operator can only forward one car at a time, and he has a fixed rate at which he can operate. Okay? So if the cars are coming at a faster rate, what will happen? The queue size will become larger. At non-peak hours, let's say in the afternoon, office hours have already gone. One car will stroll in at a time. The operator will quickly process it, forward it, and then there is no other car. What will be the queue size? 0. Most of the time, 0 or 1. Okay? So what is the queue size is not a fixed size. It depends upon the arrival rate of traffic at any node and the processing capacity of that node. Now, typically the processing capacity of the node is fixed. It's determined by the CPU of that switch, but the incoming rate could vary. Right? So queuing happens whenever work arrives faster than it can be serviced. This typically will happen in real life scenarios in peak hours. In a packet network, we call this peak hours from a packet network perspective. Whenever there is more traffic in the network, queues will form in intermediate routers and switches. In intermediate packet switches, queues will form. So any packet which is coming in will get queued at the end of queue. And the forwarding function will occur on the top of queue. So one at a time, they are getting processed, just like at a toll plaza. So this in a packet switch network is another form of delay. So right now we talked about transmission delay. This delay is called a queuing delay. So every packet, when it goes one hop to the next hop to the next hop, experiences what we call as the queuing delay. And the queuing delay could be variable. Right? Unlike L by R, which was constant transmission delay, queuing delay is different, variable, depending upon the time of day, which determines the size of the queue. Okay, so this is another source of delay in a packet network. Not just delay, this is also a source of packet loss, something that Vipul just asked. If no node or no network switch can have infinite size of data buffers. So the number of data buffers that my network switch will have is predefined and fixed. If the arrival rate remains large for a sufficiently large amount of time compared to the processing rate, the queue will keep on filling up. At some point in time get completely filled up, and any subsequent packet that reaches this switch, what will happen? There'll be no memory, no data buffers to hold, and those packets will, what will happen? They'll be dropped or lost. So lost packets is by design a possibility in a packet switch network. Vipul, what you asked, packet loss is by design expected to happen in a packet switch network when under peak traffic conditions. Under peak traffic conditions, it's possible that packets will get lost. Okay, so this is one of the key ingredients that needs to be taken into consideration when we design a network. How do I design a store and forward packet switched network such that the loss of packet is minimum? What should be the data buffer capacity at each intermediate network switch? What should be the CPU capacity of a network switch? Depending upon the incoming links and their transmission rates. Okay? All of this is a network design problem. How should I design my network so that the packet loss can be minimized? Okay? Irrespective of what I do, packet loss in a packet switch network is never zero for various reasons. I often don't want to have a zero packet loss rate because it unnecessarily over designs my network. It increases or bloats the cost of designing my network. We'll come to this at some point in time. But all that I'm saying at this point in time is in a packet switch network, packet loss is a reality. It can never be zero. Okay. So that's what queuing causes. It causes a packet queuing delay. It introduces a packet queuing delay. It can also lead to packet loss in a packet switch network. Now that brings us to the very important question of how does then packet switching compare against circuit switching? And that's the question we just had from Dayanand. What's the difference between packet switching and circuit? So what we've discussed so far is packet switching. I'm taking chunks of data called packets and switching them using a store and forward mechanism. How is it different from circuit switching? Now, as I said, circuit switching is a term that initially was coined for voice networks, right? So old telephony networks, even today, the plain old telephony systems, right? Not your broadband telephony network. So if you're taking an Airtel broadband connection, then it also gives you it will give you internet, it will give you TV, it will give you telephone connection, also all on the same channel. Right? That may not necessarily be a plain old telephony system. Right? So not that, but think of the old telephony networks, which were basically meant to have a telephone at your home, a twisted copper cable which will connect the telephone using a dedicated twisting copper cable to what we used to call as the local exchange, LEX. And then the local exchange used to connect to a larger exchange called the trunk exchange. And then one trunk exchange in one city will connect to another trunk exchange in the other city. And that, so let's say, let me take an example. This is me calling Dayanand at his home. Dayanand has a telephone line. I am in Gurgaon. Dayanand is in Bangalore. I don't know where you are, Dayanand. I'm just taking an example. But when I call, my call connects to the local exchange of my city, whatever my city is ABC. It then goes to the trunk exchange of, let's say, Gurgaon. From Gurgaon, the trunk exchange connects to the trunk exchange in Bangalore. From Bangalore trunk exchange, the call goes to the local exchange of Dayanand's city, which may be DEF. This is the locality he stays in. And then from the local exchange, there's this last mile copper cable that connects to his telephone. So these were the old telephony networks. Now in these telephony networks, As you can see, the last mile was always dedicated. Between your telephone to your local exchange, it is always a dedicated copper cable meant to carry just your voice samples. From the local exchange to the trunk exchange, from trunk exchange to this next trunk exchange, and from the final trunk exchange to the local exchange, there can be multiple, there are communication links of varying capacity. Okay? Now, when I reserve certain resource, okay, so when I call Dayanand, this last mile is already dedicated to me. Only my voice samples will be carried to the local exchange. But between the local exchange to the trunk exchange, let's say there's a high capacity communication link. Okay? There's a high capacity communication link. This is me, let's say, instead of the computer, think of it like the telephone. So this is me calling Dayanand. Dayanand is here. So this is a dedicated line. Then between my local exchange to the trunk exchange, there's a lot of capacity in this communication. But what am I doing? I am reserving some bandwidth or some carrying capacity on this link specifically just for me. Sorry, not for me, for the call between me and Dayanand. Okay. Now a telephonic call, take it from me right now, required 64 kilobits per second of data carrying capacity. This comes from a lot of factors. When I take an analog voice sample, this is an analog voice sample. Sound is analog by nature, right? It's analog. People who understand what is analog, what is digital. But these exchanges carry digital traffic. All our telephony networks are digitized. Right? So what do? I take an analog sample of sound. I do an analog to digital conversion. When I do an analog to digital conversion, I go through a function called sampling. So normally sampling in voice networks is done at 8,000 samples per second. Every sample is represented using 8 bits of information. So this gives us a voice requirement of 64 kilobits per second. If you understand this conversion, it's fine. If you don't understand, just remember that for carrying voice, digitized voice, when I take an analog voice sample, convert it into digital, in plain old telephony systems, it required 64 kilobits per second of capacity. So if I were to reserve 64 kbps of capacity in this link, it's like saying that a circuit has been reserved for carrying data for the call between me and Daya. Same thing happens between the trunk exchange to Daya's local exchange. A 64 kbps of capacity is reserved. Think of each of these sublines as 64 kbps. There are maybe 4 or 5 lines. Okay? So if I reserve that capacity for me, then what am I essentially doing? I'm setting up a dedicated end-to-end circuit between myself and Dayanand. If I use it, which means if I'm talking, I will be using it, some voice will be flowing on top of it. If I don't use it, if I'm silent, what will happen? The circuit will remain established. The bandwidth will remain reserved for the call between me and Dayanand. Nothing will flow on that link, on that circuit. But what will happen? I'll be billed for it. Because the resources, what is the resources? Capacity. The capacity or the resources have been reserved for the call between the source and the destination. So whether I speak or I don't speak, because the resources are reserved, I have to pay for those resources. That is the reason why you would have seen the billing for voice calls happens on a per second basis. Whereas the billing for data transfer happens on a per kilobyte basis. This is more of a pay-per-use model. This is more of a duration-based model. Why? Because In a voice, when I'm using circuit switching, I am reserving the resources irrespective of whether I use it or not. So I have to pay for those resources, and therefore the per second billing. Right? Now, the benefit of reserving resources is what? There are no chances of a packet loss. There is always sufficient capacity reserved in the network to carry my voice samples, because the voice samples that I will generate will not be more than 64 kbps. And because 64 kbps of throughput is reserved on the end-to-end path between me and Dayanand, whenever I speak something, there is always be bandwidth to carry it over the dedicated circuit set up for our call, and there'll be no packet loss. So voice or voice networks, they are not immune to packet losses. What do I mean by that? So think of a voice communication. If the network is lossy, which happens often when you, for example, make a data call, a WhatsApp call, let's say. If the network is lossy, what will happen? I speak a statement of English, and let's say intermittently, some of the words just get lost. So what will you hear? A broken sentence on the other end, sometimes making it difficult to understand. Okay? So voice networks are not too tolerant to such losses, and therefore circuit switching is a better technique for carrying voice traffic. If, of course, I want to have good quality voice communication where voice is not breaking in between. But it is costly because of the per second billing, because resources are being reserved. So this, where I reserve resources between the end-to-end path, I'm essentially setting up a circuit. We call it a circuit. A circuit is established between the source and the destination. And this kind of switching method is called circuit switching. In the packet switching network, what were we doing? We were not reserving any resources. So if A was sending some data to the access switch and B was sending some data, the packets that were coming at this access switch, how were they being handled? In a best effort manner. As long as I have data buffers, I'll queue your packet. And then when the time comes for your packet to be forwarded, I'll forward it. If the queue gets full, bad luck for you. Your packet is going to get lost. So a packet switching function is more of a best effort. If I have capacity, I will buffer your packet and forward it. If I run out of data buffers, your packet will get lost. So packet switching is often considered the best effort switching technique, whereas circuit switching is a guaranteed switching technique. Okay? So in this diagram, as we said, every link has 4 circuits. We are calling it circuit. Okay? A call gets 1 circuit in each of the links. So in the top between the local exchange to the trunk exchange, it gets the second circuit. Between the trunk exchange to the next local exchange, this is LEX1, this is LEX2, it gets the first circuit. So when the traffic is coming on the second circuit, this switch will switch it onto the first circuit. From the second circuit, it switches it to the first circuit. This is called circuit switching, so that it reaches the right person. An end-to-end circuit is established, intermediate switches are switching the circuits, and the call is reaching the right destination. This is called circuit switching. Historically, until this whole switching was not automated, it was often done manually by operators sitting in the local exchange. You might have seen it in movies. Okay, I'm connecting you to the destination. They'll actually take some cables, physically plug in a cable in one of the ports and the cable in the other port. That's circuit switching. I'm connecting your circuit to the other circuit. Today, it's all automated. This is what circuit switching is. There are dedicated resources. There is no sharing. So it gives a circuit like dedicated or guaranteed performance. And if there is no traffic, then the circuit remains idle. There is no sharing. It's not as if my circuit is idle, somebody else can use it at that time. So as I said, this is a commonly used technique in traditional telephony networks. Okay. On the contrary, what we were just discussing is packet switching, where multiple users could be connected to the next hop access switch. Let's say in this example, there are n users. All of them are connected to the next hop switch. Now, this is a very interesting example. I have n users. Each user is connected to the next hop access switch using a 1 gigabit per second communication link. Sorry. Using a 100 MB, using a 1 gigabit per second communication link. And the access switch is connected to the next hop router, let's say another switch next up, also using a 1 gigabit per second link. Okay? Now, what I know is that of all of these end users, they're not always active. That is what we know in a communication network. Right? When I sit on my computer, it's not as if I'm browsing the internet all the time. We're not always active. So I know that each of these end users, statistically speaking, I have measured that each user, when they are active, they transmit traffic at 100 Mbps. Okay, but they're not always active. They are active only 10% of the time. So it's like saying in 1 hour, 6 minutes of the time I am exchanging data with the network. Either an email is coming, or I'm initiating an HTTP web request, or I'm doing an FTP file transfer. So in 1 hour, 6 minutes of data transfer is happening. Now, when that 6 minutes happens, of course, it's staggered. This is when I do that data transfer, I'm considered to be active. Okay. So what I know is that when a user is active, they typically transmit at 100 megabits per second, but they're active only 10% of the time. This is a typical packet user's behavior. Okay. Now, if this is the kind of network that we have, which is what we actually have in data network, how many users can your network support if we were to use circuit switching instead of using packet switching? Okay. Now, do you want to attempt this? I have 1 gigabit per second link connecting my first switch to the next second switch. This is a 1 gigabit per second. When one user is active, they transmit at 100 Mbps. How many users can use this network if I want to set up this network as a circuit switch network? How many users? What can be the value of n? Vipul has it right, 10. A lot of you have it right. Good. Prashant, yeah, okay. A lot of you. Prashant, Mohsen, Ramkumar. Yeah, okay. Okay. Parshvanathan says 1, but I don't know why you say 1. That's not correct. 10. Maybe it's a typo. You just can type it. Okay. So if I have 1 gigabit per second, yeah, okay. If you want to use MB to KGB computation using 1024, yes, you'll have a slightly different value. Let's assume simple, right? So 10 users is what I can simply support, because 10 into 100 Mbps, I'm doing the simple calculation, not using the bit calculation. So 10 into 100 Mbps, I'm saying is 1 gigabit per second. I'm using 1000 Mbps equal to 1 Gbps instead of 1024, keeping it simple. Okay. So circuit switching, I can use 10 users, because every user, there has to be no packet loss. I'll reserve resources for them. So as soon as the first user comes in, I'll reserve 100 Mbps on this link. So only 10 users can be supported. The 11th one, I'll have to say, all resources on this path are busy. Please try after some time. That's the kind of message I get on a telephone email. But in a packet switch network, what do I do? I also take into account this second factor. Active only 10% of the time. Okay. So Sparsh is saying 100 users in the packet switch. Actually, it's a little more tricky, Sparsh. Right? the 10% is not directly taken because the 10% there's also a probabilistic factor. It's not as if it's also possible that all of them become active at the same time, right? Even though when they're active, they're only active 10% of the time, but they can still become active at the same time. So what we do in packet switching is we do a probabilistic calculation. Okay. Our problem is, what is the probability that n equal to some value? Let's say here we are saying 35. If n were equal to 35, what is the probability that of these 35 users, more than 10 users become active at the same time? That's the problem I'm trying to solve. So I know they're active only 10% of the time. What can be the value of n? And this value of n is determined using a probabilistic measure. So I'm giving you some values, not explaining. I mean, this is maths. So with 35 users, if I say n is equal to 35, the probability that more than 10 users will be active at the same time is actually less than 0.0004. So what we're basically saying is that even if I choose n equal to 35, my network can still sustain itself. Why? Because the probability that more than 10 will be active at the same time is minimal, is very small. And if that happens, my switch has the capacity to buffer certain packets. It has what we call as some data queues. So for some amount of time, it's possible that more than 10 users are simultaneously active, which means the data traffic arrival rate will be higher than the servicing rate, which means for some time my queue will fill up. But as long as, once again, the number of active users goes below 10, this queue will eventually be serviced. I may not have packet loss. Okay, so this is a technique because it's based on statistics. It's using probability theory to determine what should be a good value of n, right? So that the probability of packet loss is minimized. Right? It also helps me, by the way, determine how much queues should I maintain on a network switch. This kind of a technique of network design or traffic multiplexing, what are we doing? We're multiplexing traffic from n users onto a single outgoing link. This technique of multiplexing traffic is called statistical multiplexing. So this is a term that we use in packet switch network. The concept, it's a concept used in packet switch network. The concept of statistical multiplexing, which means what should be the value of n so that the packet loss can be minimized, not made zero. See, I could have made it zero, as I said, but that's not my intention. If I make it zero, I will only support 10 users. But that's diminishing the utilization of my packet switch network. If I can live with the probability of 0.0004, or better still, handle that by maintaining some buffers in the intermediate network switches, I can support a larger value of users, which means my network utilization is better. I can support more number of users with the same network, thereby distributing or reducing the cost per user. So statistical multiplexing helps me, or packet switching helps me reduce the cost per user, improve network utilization, while living with some risk of packet loss. Yes, Amruta. So that's what I said. Data buffering capacity will matter in case of packet switching. When the number of users becomes greater than 10, the arrival rate of traffic at the switch will be larger than what it can send out. Because when it is, let's say 11, what will be the incoming traffic rate? 1.1 gigabit per second. What is going out? 1. So some packets will get buffered. The queue will start to fill in. As long as my queue can handle that and this arrival rate reduces after some time, there'll be no buffer overflow and there'll be no packet loss. Worst case, there could be some packet losses. I'm willing to live with that. That is the kind of network I'm designing. Okay? So I'm designing a network where I'm saying I want to have better utilization of the network resources. Therefore, I'm admitting more number of users with a statistical computation telling me that the chances that there'll be packet losses is very low. And if it happens, then we'll live with it and we'll look at alternate techniques to handle those packet losses. We'll probably handle it at higher layers, what we call as the transport layer. I will come to that later. Okay, so this is how this is the ideology or the mindset when designing a packet switching network with a circuit switch network. In a circuit switch network, I am playing it very safe. I want no losses, guaranteed traffic, even if I have the network resources have to lie idle for a lot of time. But what it translates to is higher billing costs for user. Packet switch network, I'm making use of statistics or probability theory to give a best effort experience to my users, but at a very low cost by increasing the utilization of my network resources. That's the difference. Okay, so that should answer, I think, the earlier question about how is packet switching different from circuit switching. Okay, now does that mean that packet switching is a slam dunk winner? Nobody should look at circuit switching? Well, practically speaking, I would say it's becoming a reality. Every communication network today is moving towards packet switching. Right? Look at the mobile networks. When we started using mobile networks, the first mobile networks were GSM networks. Right? We also call them second generation of mobile networks. They were circuit switch networks. Right? Third generation of mobile networks introduced an option. They had both circuit switching and packet switching. From fourth generation or LTE onwards, there is no circuit switching in the core part of your mobile network. The core part of the LTE mobile network has completely moved towards packet switching. Okay? The same is happening in a variety of communication networks. Okay? Slowly and gradually, we are moving from circuit switching to packet switching because of cost. When I try to make a call to somebody in US, I no longer pay IST rates. I would rather make a WhatsApp call. Okay? I know that making an IST trunk call will give me better voice quality, but it also costs. Whereas when I make a WhatsApp call, there may be echo, sometimes some losses of some broken sentences, but it comes at free, nearly free. So I use it. Right? So it's a matter of choice. So it's not as if packet switching is a slam dunk winner when it comes to, let's say, corporate communications. And in corporates, I want better quality even at the cost. I will still continue to use circuit switching. Right. Tanuja, yes, defense may still continue to use circuit switching because of the reliability of communication. So wherever reliability is of great concern, circuit switching is a slam dunk winner. I will pay more for reliability. But wherever I can live with a slightly lower reliability and quality, but cost is a major concern, I will move towards packet switching. Okay. So in general, packet switching is great for bursty traffic, okay? Which means sometimes you have data to send, other times you don't have. It's great for those kind of applications, bursty applications, because we can get better benefit out of resource sharing because everybody's traffic is bursty in nature. So user A is sending traffic. If I draw his traffic graph over time, this is time, this is traffic rate, this is traffic. It may be something like this. This is for A. If I draw it for B, it might be something like this. Now, if I superimpose the two together, wherever there is lack of utilization, there is a peak. Wherever there is high utilization of A, B is sending nothing. So I can do more resource sharing using the same resources. Plus the fact that it's simpler. I don't need to set up a call. And in a telephony network, what happens? I dial a number. For some time, some signaling is happening in the network. What is happening? A call is getting established. Resources are getting reserved. It's called call setup. It takes some time before I can hear the ringing, and then somebody picks up the call, and then the call is connected. In a packet switch network, as soon as I have data, I immediately start sending. There is no process of call setup because there is no reservation of resources. So it's simpler. But as we said, there is its best effort in nature. So there is possibility of packet delay because of queues filling up, and queuing contribute to queuing delays. There is possibility of packet losses due to buffer overflows. So I do need to think of, and we will talk about these protocols later, I do need to think of protocols that can support providing reliable data transfer and handle packet losses when congestion occurs. Okay? So there can be certain applications which cannot live with packet loss. For example, file transfer. If I'm transferring a file over a packet data network, and even a single packet loss happens, the entire file is corrupted. File transfer cannot live with packet loss. So I do need a protocol which can handle packet losses. We will talk about this later in subsequent classes. Right? So packet switching is good for bursty traffic because it's simpler and it supports more number of users in the same resource. But I do need to have protocols that can support reliable data transfer for specific applications that need it, like file transfer. How do I do it? We'll talk about it later. Okay. Now, is it possible to use a packet switch network and provide a circuit switch like behavior? Right? It is complicated, but over a period of time, because packet switch networks are becoming very popular, techniques have been defined or designed to try to make packet switching as circuit-like as possible. A very important example is voice over IP. Voice over IP is uses a suite of protocols, right, which tries to use a variety of techniques like priority-based switching. So when you have queues in intermediate switches, instead of having a single service all kind of a queue, have multiple queues based on priority of traffic. So we call this priority-based queuing. It's like having a toll plaza and you have a lot of toll gates. Some of them are for general public, which is best effort. Some toll plazas are reserved for emergency traffic, ambulance, police vehicles, which require a better SLA, service level agreement. And some may be reserved for VIP traffic. Let's say the chief minister is passing by and he doesn't want to be in the general queue. What are these? Priority-based queues. So I can implement priority-based queuing as a simple method to improve the quality, and I can put circuit traffic like voice traffic into higher priority queues in intermediate switches. It's a possibility, something that VoIP can do. Right? So there are various techniques, including priority-based switching, including there's a protocol called RSVP. It's a reservation protocol where let's say in an enterprise network, in my own enterprise network, I am using packet switching, but I do want to provide circuit-like behavior. So I can implement RSVP as a protocol where for circuit traffic, RSVP can reserve some resources in the packet switch network. Okay. There's also another technique called type of service. It's called distributed. So the type of service which is used to handle or switch It's once again used for priority-based queuing. Based on the type of service, I provide priority handling for some traffic and low best effort handling for other traffic. So there are techniques. It's complicated, but some techniques have been tried to be built to provide circuit-like behavior as much as possible, even in packet switch networks. There are a suite of protocols which attempt to do that. Okay. But general packet switching without this add-on suite of protocols is what we call as best effort in nature. Okay, so that should answer a lot of questions that came in. What is packet switching? What is circuit switching? Plus, it introduces a lot of very fundamental concepts of what is store and forward in a packet switch network, and why is packet loss happening in a packet switch network? Why are delays and variable delays getting introduced because of queuing? Right? Okay. Now let's come back to the internet, and we said the internet is a network of networks. The ISPs are helping connect a lot of these access networks together, making it an internet or a network of networks, so that any two hosts anywhere in the world can send packets to each other. And the resulting network of networks is, of course, becoming a very complex network. But it is still working. We've seen the internet work. And it's been made to work because it's an evolution that is being driven by economics and national policies. Right? Who connects to what ISP? How do Indian users connect to users in US via which ISPs? All of it is a lot driven by economics, which means which ISP is providing me what kind of a billing plan, and also national policy that time. I don't want to send traffic from India to US via any intermediate network that passes through Pakistan. Let's say it could be a national policy. Right? So the resulting network of network is becoming very complex, and often it is driven by economics, which means cost, as well as national policies. Okay? So that is what essentially is the internet. Now, if we look at the internet structure, okay, we are saying it's a network of networks. So essentially, we are saying there are access networks all across the globe. My home network is an access network. My office enterprise network is an access network. The mobile network that I connect to is an access network. Now, all of these access networks, we are saying the ISPs are helping connect these access networks together. That's how the internet is forming. But there are millions of these access networks. How do you connect all of them together to form the internet? I can do something like this. Every access network connects to every other. Mesh connectivity. Is it feasible? It's not feasible. It's not sustainable. Every access network cannot connect to every other access network in the globe. It would mean every network has to maintain millions of connections to sustain that connectivity. Not possible. Right? It doesn't scale because we require order of n square connections to sustain this kind of a topology of the internet. So this topology is not a sustainable topology. So what do? What we can do is have a global internet service provider. Right? And all of these access networks can create what is called a hub and spoke, sometimes also called a star topology or a hub and spoke topology. Every access network can connect to the global ISP, and the global ISP can then be the interconnection point. It can, if there's traffic from any one access network to any other access network, the global ISP can help connect. How many connections do I need in this kind of a topology? Order of n, where n is the number of access networks. So from order n square, I have come down to order n. Correct? And this is a more sustainable network model. Guys, give me just 1 second. I'll be back. Just one, not 1 second, but half a minute. I'll just come back in a minute. Sorry, I'm back. Right? So this model has, or this topology, from a mesh topology to a hub and spoke topology, has immediately reduced the number of connections that I need to maintain. Right? Now here, the access networks are the customers of the global ISP, and the global ISP is kind of a service provider. So there is some kind of an economic agreement between the access network and the global ISP. Like the access network is saying, I have 1,000 customers. This one is saying, I have 10 customers. He's saying, I am a large one. I have 100,000 customers. Each of them, based on the customer base, are agreeing a pricing policy with the global ISP saying, for every kilobyte of data that I send via your network, this is how much I'll pay. So the more the subscriber base I have as an access network, the bigger my bargaining power. Right? It's economies of scale. So every ISP is creating an economic agreement with the global ISP, creating it a economically viable business for the global ISP. But as soon as the business, if the business is viable for one global ISP, don't you think a lot of people will jump into the game? If there's an Amazon, someone like a Flipkart will jump into the game. And someone like a Reliance will definitely also throw in the towel because everybody wants a piece of the pie. Right? So if it's an economically viable business to be a global ISP, there is bound to be competitors. And when they are competitors, it means there are going to be multiple ISPs. So some access networks will tie up with some ISPs. Other access networks will tie up with other ISPs. Right? Now, this would make the entire internet fragmented until when? Until the point when these ISPs A, B, and C, who are global ISPs or the three large global ISPs, until the point that they themselves connect to each other, the internet will not be wholly connected. So what we need for the internet structure to be completely connected is that these global ISPs connect to each other. And this is what we call as the backbone of the internet. The global ISPs connect to each other via what are called as the IXP points or the internet exchange points. And this is what is the structure of the internet that we have. Right? Sometimes two ISPs routers may also have a direct peering link between them. So that traffic between ISP-B and ISP-C can also go over this peering link. So they have kind of a mutual agreement that traffic between us can go over a mutual link rather than going over the internet backbone. They call it the peering link. Okay? So this is what the internet architecture has become. Now, between the access network and the global ISPs, there can also be some regional ISPs. So if the country is large, let's say something like India, there'll be a lot of smaller access service providers, access networks, like our enterprise networks, but there'll be a lot of regional ISPs like Geos and Airtels and VSNLs and so on. So eventually, the internet structure is something like this. End host like us, somebody like me, connects to an access network, which connects to a regional ISP, who connects to a global ISP, and that's how I get connected to the rest of the internet. Okay. In between these global ISPs, somewhere the content provider network will exist. So people like YouTubes and Netflixes and all these content providers on top of this internet, they will like to superimpose or set up their own content provider network so that their content, Netflix content or YouTube content, can reach all subscribers globally. How this content provider network is getting set up on the internet, this will be a case study, which we will take after we've gone through the topics of data center networks, after we've discussed how multi-site data centers are set up, then we will come back to big content provider networks and we'll see how content provider networks are set up over the internet. Okay, so we'll come to this topic later. This is what the internet structure is. Okay, so it's a network of network. And if I try to draw what I was showing in the previous slide slightly differently, this is how I can redraw it and show it more like what a hierarchical structure. So the internet structure is actually a hierarchical structure with the access ISPs at the lowest level of hierarchy, the regional ISPs at the next level of hierarchy, and then the global ISPs, the tier 1 ISPs at the highest level of hierarchy. And then content providers like Google, they are trying to set up economic connections, agreements with tier 1 ISPs, sometimes also with access ISPs, sometimes with also regional ISPs, to make sure that their content like YouTube is getting provided to everyone across the globe. So that's the content delivery network, which I said. So this is another way of depicting the internet structure as a hierarchical structure. Okay. So Aruna has a comment to make. Yes, she says the undersea cables that are connecting across continents, they're actually the internet switching point, the IXPs. Okay. So this is what the internet structure is. Now that we understand what the internet structure is, it is easy to come back to our discussion on what causes delays in a communication network like the internet. What is the source of packet delay? What is the source of packet loss? So we've already said that there are packet queues in intermediate network switches and routers, and packets wait for their turn in these queues until their turn comes for transmission. So any queue by default is a first in, first out. Okay, Tanuja wants me to summarize the previous slide again. This is nothing different, Tanuja, than what I was showing on this slide. So gradually we introduced the structure of the internet, saying how access networks and regional ISPs and global ISPs connect to each other. I just drew it in a slightly different fashion by saying, okay, I am here. I'm a small leaf here. You are somewhere here. You're another small leaf. We connect to an access ISP in our cities. Our access ISPs might be connected to a regional ISP, and that's how we may be connected together. Or if you are in US and I am in India, then we may actually be getting connected via a tier 1 ISP. So it's only the whole internet is actually a hierarchical structure. And this is how it's a network of networks, some small networks, some larger size networks, some very large networks, all connected to each other based on certain economic agreements. A regional ISP will have an economic agreement with a tier 1 ISP saying, I have so many customers under me. He'll put together all his access ISP customers and say, I have so much customers under me. I will pay you only so many paise per kilobytes of traffic that I send via your network. Right? Amit wants examples of tier 1 ISPs and regional ISPs. Tier 1 ISP is very few across the globe. AT&T is a tier 1 ISP. Pirate is. In India, you can call BSNL a tier 1 ISP. Right? Regional ISPs are more like your Airtels and Reliance, Geo Fibers, who are more national level in that sense. An access ISP could be as small as your enterprise network, or let's say Vodafone's mobile network could be an access ISP. Okay, so Vodafone's access network could connect to the VSNL network, which is a regional ISP, which could connect to AT&T or Spirent in US. These are examples of small to larger internet service providers. It's basically by volume, okay, by number of subscribers that they have. Okay, so internet is, as we said, a network of network, and it's a hierarchical structure. Okay? And we've also learned that packet delays occur because of buffers and Loss could also happen when packets are queued. So this, okay. So this slide is kind of introducing other aspects of packet delay. So what have we so far said? We've already talked about transmission delay. Right? What is transmission delay? I pick up a packet of L bits and I transmit it on a link of RBPS. That's the transmission delay of L by R. We've also introduced queuing delay, where we said packets have to wait in buffers, because of which they suffer a variable delay called the queuing delay. It will depend upon the size of the queue, which can vary from time to time, and therefore it's a variable delay. But are those the only two sources of packet delay in a packet switch network? No. There are actually two more. What are those? What is it that we did not account for? We never accounted for the propagation delay. What we said was I pick up a packet which is L bits and I start to put these bits on the transmission lane until I can empty that packet. That's the transmission delay. But every bit that I put on the communication link has to flow from the source and reach the destination. Every bit has to do this. What is this? This is called the propagation delay. What will it depend upon? It will depend upon the distance of the link. The propagation delay will differ if this link is an undersea link, like Tanuja said. No, sorry, like Aruna said. If it's an undersea link, the distance is large. The propagation delay will be larger. But if it's a local link between my my laptop to my Wi-Fi access point, the propagation delay will be smaller. It's dependent on distance. So the transmission is I pick up a bit on the packet and put it on the transmission link. But for that bit to flow towards the other end is the propagation delay. And the propagation delay, sorry, let me first talk about the propagation delay. So while the transmission delay is dependent upon the transmission rate, as we've already said, it's L by R, the propagation delay depends upon the length of the physical link and the type of communication link. The type of communication link will define the speed of propagation, the propagation speed. Let's say if it's an optical cable, then the speed of propagation will be the speed of light. So something like 2 into 10 raised by 8 meters per second. Right? So the propagation time, it's the normal formula of physics. Speed is equal to distance upon time. That's what we learned in physics. So time or propagation delay is equal to distance of the physical link divided by the propagation speed. So propagation delay depends upon not just the length of the link, but the propagation speed. The propagation speed depends upon the kind of link. Is it an optical cable? So it's light wave communication. Or if it's a copper cable and it's electrical communication, what is the propagation speed for the bits? That contributes to the propagation delay. Right? Okay. There's a fourth source. So far we said there's a transmission delay, there's a propagation delay, and there's also a queuing delay. But there's a fourth source of delay, which is called the nodal processing delay. What is that? So every switch, right, when the packet goes into the queue, it's into the queue, that delay is called the queuing delay. But when this switch picks up the packet from the head of queue, so I pick this up, what do I do for forwarding? I look at the packet header, I'll do a forwarding table lookup, I'll match that header in a forwarding table, and then I say, this is the outgoing link that the packet needs to go to, and then I forward it. What am I doing? I am doing some processing. What will be the speed of processing depend upon? The CPU in this network appliance or this network switch. This is the processing delay called the nodal processing delay. So the overall delay that any packet faces in at any point, hop by hop, and any hop is sum total. So if I say at every node, what is the total delay at every node, at every hop in the network path? What is the total delay that a packet faces? Let's call it the nodal delay, the nodal. The total delay that occurs at every node. It's the total of the processing delay, dproc, which is, as we said, dependent on the CPU power of the switch. The queuing delay dependent on the queue size, current queue size. The transmission delay, which is L by R, and the propagation delay, which is D by S. At every hop, this is the delay a packet faces. And this delay will keep on adding hop by hop until the packet can go from the source to the destination. Okay. If once again I go back to the toll plaza analogy to help you explain this further. Look at a caravan analogy. So now there's not one car, but a caravan of 10 cars. So if the president of India is traveling from one city to the other, it's not one car, it will be a whole caravan of cars that will be going. He'll be somewhere in the middle of the caravan, and then there'll be some cars ahead of him, some trailing him. Okay? So think of the 10-car caravan as equivalent to 10 bits of data. And the entire caravan is like a packet. Okay. The toll booth is like an intermediate switch. So think of every car as a bit of information, the caravan as a packet, and every toll plaza as an intermediate switch. Now let's say the toll booth takes 12 seconds of time to service each car. Right? That's what the processing delay. Right? The human sitting at the toll booth takes some amount of time to process the car. Think of it like the CPU. The human is the CPU processing. So it takes 12 seconds to service each car. And the car has between two toll booths, from the first toll booth to the next toll booth, which is like from one switch to the other switch. Every car that has been processed needs to propagate further 100 kilometers. And let's say these cars are very high-end cars. It's a fleet of Mercedes, and the roads are very good between the tolls, and the cars can run at 100 kilometers per hour. So they've decided we'll go at a speed of 100 kilometers per hour. All of them had made that decision. So they're propagating at 100 kilometers per hour. The question is, how long will it take until the caravan is lined up before the second toll booth? Every car takes 12 seconds to process. Actually, here the 12 seconds includes two things: dproc plus dtrans also, because we don't have any equivalent of trans here. Right? So we're saying, okay, transmission time is the person is actually doing what he has to do, take money or whatever, and then open up the toll plaza, and then he lets it go, the car go. The car will take some finite time to cross the toll plaza. So that's the T-trans. And there's a dproc. And put together, this is 12 seconds. Dproc plus dtrans. Propagation is distance 100 kilometer upon speed 100 kilometer per hour. Okay. How long until the toll plaza? So I already see an answer from Siddharth, 124 minutes. Right? So let's calculate. The time to push the entire packet through the first toll plaza onto the highway is what? Every car takes 12 seconds to process, which is dproc plus dtrans. And there are 10 bits or 10 cars. So 120 seconds is the time it will take to push the entire caravan from the first toll booth onto the highway. And the time it takes for the last car, this last car, after it has been pushed by this toll plaza onto the highway. So 120 seconds is what I'll take from the first car to the last car to be pushed. And the last car, the time it will take to reach the next toll plaza is what? 1 hour. 100 kilometers upon 100 kilometers per hour. So what is the total time, right? Vipul has it right. 62 minutes. Yeah, a lot of you have it right now. 1 hour, 2 minutes. Is what it will take for the entire caravan now to be lined up before the second toll. Okay. So this is how the data is also getting processed. Dproc plus dtrans plus depropagation. Right? Plus here we did not take queue into account because it's a VIP caravan. But had there been a queue, there would also have been a queuing delay at the toll plaza. But that's a simple addition. Had I said the first toll plaza has a queue ahead, and to service that queue, it will take another 120 seconds because it's a 10 queue ahead. You will add just 120 seconds more to this, and you'll say 64 minutes, including the queuing delay. So that's how we work. Now, I'm just trying to interestingly twist the same example a little bit. Everything else is the same, just that these cars. Okay, Payal did not get it. I'm sorry, in the interest of time, Payal, I'll just leave it. I'll give you these slides. You can go through it. It's not complex. It's very simple maths. You can take your time after the class. Just go through these slides. I'm sure you'll figure out. If you don't, come back to me in the next class. I'll answer it again. I'm sure you'll find it out. So let me just keep on proceeding because we just have 4 more minutes. I just want to come to a logical conclusion. I've just interestingly twisted the example and said, okay, instead of running at 100 kilometers per hour, these cars are super modern cars and they can run at 1000 kilometers per hour. And even the highway is very, very good. But the person sitting at the toll plaza has is an old fellow and he takes 1 minute to service every car. He's slow. So what has come down? The CPU speed has come down. The dproc has increased. Right? And essentially we're saying dproc plus dtrans put together is now 1 minute per car. The question is, will cars start to arrive at the second toll booth even before all cars have been serviced at the first booth? And the answer is yes. I'll leave it for you to calculate, but you can easily calculate. You'll see after 7 minutes, the first car will arrive at the second booth because it's traveling at 1000 kilometers per hour. After 7 minutes, the first car will arrive at the next toll booth. But there'll be still 3 cars because in 7 minutes, only 7 cars would have crossed this toll booth. 1 minute is the time it takes. There'll still be 3 cars at the first booth. Why did I make this twist? To show you the store and forward example. Remember that slide where I showed a packet was half empty here and half full at the next switch. So this was a packet which was being transmitted and I was showing it's half empty, half full. And here it's already been half received, but the rest of the half has to be received. That is where I explained the store and forward concept. So the store and forward concept can occur when dproc plus dtrans plus the queuing delay is larger than your propagation speed, especially in the smaller links in a small network, let's say within my home, the propagation of bits will happen very quick. So it's possible for some bits of the packet to already reach the next hop and the rest of the packet might still be under process. The rest of the bits in the packet might still be under process. Okay, so that's a possibility. So I'll stop here. Already at the end of the class. Okay. So this is something I probably might skip. We don't need this, the packet queuing delay and how it's more of a statistical function. The arrival, it's basically, it's just an example which shows there's in statistical multiplexing, we actually compute something called a traffic intensity, which is the ratio of the arrival rate of bits to the service rate of bits. L into A is L is the packet length. A is the average packet arrival rate. So we say L into A is the average rate of bits arriving. R is the service rate of bits. We call this the traffic intensity. Now, if the traffic intensity is approximately 0, right, we say that the queuing delay is going to be very, very small. It's basically like saying there is no queue. Anybody who arrives is getting serviced. If the LA is tending to 1, so between 0 to 1, the queue is continuously increasing. As it approaches 1, we say that the queuing delay is quite large by now. But as soon as LA by R, which is the traffic intensity, increases beyond 1, it's where we are saying that the work is arriving much faster than how it can be serviced. So the delay will become infinite. It is for such cases that no matter how many buffers you have, eventually you will end up into packet loss condition. So when we design a network, we look at what is the traffic intensity, and that is how we design a network. It's exactly like designing your roadways. What should be the thickness of my highway? Should it be an 8-lane highway or a 4-lane highway or a 3-lane highway? It's exactly how we create toll plazas. We look at the arrival rate, the service rate, calculate the traffic intensity, and then we say, okay, what will be the queuing? We look at the peak hour traffic. We look at the mean hour traffic. We look at the off-hour traffic. So designing a communication network is much like designing a lot of other practical scenarios that we see all around us in our everyday life, including a road or a toll plaza. Okay. Okay. Actually, it's the last slide if you allow me, but I think we are running out of time. So let me go take it in the next slide. I'll just show you a real life program that we use in networks to measure the link by link or hop by hop deep rock the transmission delay. Okay, so maybe I'll show you next class. It's just the last part of what I wanted to do today. Maybe next class we'll do that and then go forward with the content that I planned for the class 3. Okay, so thank you everyone. Thank you for joining in. Thank you for being interactive, answering, solving problems, giving answers, asking questions, sharing comments. For people who are still silent, I'll definitely suggest it's good to be interactive, right? So it helps me also remain motivated. Let's keep sharing knowledge, and thank you for joining. I'll see you again next week. Thank you, everyone. Bye-bye.